Welcome to the video for Lecture 10, Section 4. This goes over the non-interacting and interacting fluid flow and liquid depth in tanks in series in Section 11 of the course packet. Here is example 11-3 in the course packet. The first step is to identify the system elements. We have 3 tanks. All of the tanks are non-interacting. Tank 3 has a pump with a constant flow rate. Here are the appropriate transfer functions for the 3 tanks. We do not need to develop any. We have used them before. The first 2 transfer functions are for non-interacting tanks from page 9-6 of the course packet. The third transfer function is for a constant flow tank on page 9-7 of the course packet. Assume that we are asked to find the fluid depth in tank 3 of some unspecified input function, Q. From what we have learned, we can write the transfer function z3 over q equals the product of the transfer function q1 over q and the transfer function q2 over q1 and the transfer function z3 over q2. When we substitute in the transfer functions, we get the expression at the bottom of the page. This is the overall transfer function to find the fluid depth z in tank 3. This is all that we are asked for in this question. For example 11-4, we will use the data given here to find the time domain expression for the fluid depth in tank 3, which is Z3. We are given that the cross-sectional area for tank 1 is 1 square meter, and for tank 2 and 3 are 2 square meters. And the laminar flow resistance values are 2 seconds per square meter. The input function, the inlet flow rate into tank 1 is an impulse of magnitude 3 cubic meters. That represents the situation when 3 cubic meters of fluid is added to tank 1 in an instant. Knowing the tank cross-sectional areas and the laminar flow resistance, we can calculate the tau values. From this problem, tau 1 equals 2 seconds and tau 2 equals 4 seconds. Here is the Laplace domain expression for Z3 after we insert the value 3 for Q. The course packet shows how to find the inverse in 2 ways, by hand and by using MATLAB. If we find the inverse by hand and leave the variables in the expression, we get this time domain expression in terms of A's and taus. In this form, we can see that the solution is not stable when tau 1 equals tau 2. In our case, tau 1 equals 2 seconds and tau 2 equals 4 seconds. Here is the solution using MATLAB and the residue command shown. We can easily find the inverse after writing the partial fraction expansion using the MATLAB results. The time domain expression for the fluid depth in tank 3 is shown at the bottom of the slide. Here is a graph of tank 3 fluid depth versus time. The horizontal axis is time in seconds and the vertical axis is fluid depth in meters. Here is the sketch of the tank system for example 11-5 in section 11 of the course packet. For this problem, we have 3 tanks. Tank 1 and 2 are interacting tanks, and tank 3 are non-interacting. We are to find 2 transfer functions, Z2 over Q and Z3 over Q. As before, we write the appropriate transfer functions for each element. We will just take them from the previous work we have done. The expression for Z2 over Q we can get from page 11-6 of the course packet, and the expression of Z3 over Q2 we get from page 9-6 in the course packet. We will also use the expression for Q2 over Q, which we get from page 11-6 of the course packet. To find the transfer function of Z2 over Q, we can write the expression we have. There is no other steps necessary except substitute the values tau 1, tau 2, R1, and A1. After putting in the numbers, we get the transfer function for the fluid depth in tank 2 as Z2 over Q equals 2 over 4 times S squared plus 6 times S plus 1. That is the answer we need for this problem. Now we want to find the transfer function Z3 over Q. This transfer function equals the transfer function z3 over q2 times the transfer function q2 over q. We look up the expressions we need. One expression comes from page 9-6 and the other comes from page 11-6 for interacting tanks. After combining and substituting in the value, we get the transfer function z3 over q shown at the bottom of this slide. Now let's say we want the time-dependent expressions for the fluid height in tank 2 for the previous problem when we have a step change in the inlet flow rate. Q equals 2 cubic meters per second. The transfer function for Qs is equal to 2 over s. Please note that this s is not the abbreviation for seconds. The next step are to substitute in the expression 2 over s for Qs and solve for z2. Then we take the inverse using equations 3, 15, and 6. The time domain expression for the fluid height in tank 2 is z2 as shown at the bottom of this slide. Here we do the same thing to find the fluid depth in tank 3. There are more terms, but the process is the same. The time domain expression for the fluid height in tank 3 is shown at the bottom of the slide. Here are plots of the fluid depth in tanks 2 and 3 as a function of time in response to a positive 2 cubic meters per second step change in tank 1 inlet flow rate. Again, the horizontal axis is time and the vertical axis is fluid depth. This brings us to the end of Lecture 10, Section 4 video. Please write down any questions you might come with and bring them up in class.